Hi guys, my name is Selena, and this video will discuss the derivation of the Michaelis-Menten equation and go over the steady state assumption. So enzymes typically make reactions go faster. We can divide the enzyme catalysis reaction into two steps. First is the binding of enzyme to substrate. Second is the formation of product. Now reactions 1 and 2 have their own rate law associated with them. Now this graph depicts that if we keep the level of enzyme concentration constant, then at high substrate concentration levels, it will hit a maximum speed called Vmax. This is where all of our enzyme is going to be saturated with substrate. As aforementioned, there are two steps to enzyme catalysis. Steady state refers to the state where the concentration of ES, which is our enzyme substrate complex, is constant. This means that our formation of ES equals to the rate of loss of ES or dissociation of ES. Now, the enzyme catalysis can behave as an equilibrium reaction. It can go forwards and it can go backwards. The enzyme substrate complex doesn't have to form products and can alternatively dissociate back to enzyme and substrate molecule. However, products rarely go back to reactants, since these reactions are usually thermodynamically stable. The reverse reactions are labeled as -1 and -2. In terms of our rates, the rate of formation of ES is the sum of reaction rate 1 and -2, and these reactions lead to the formation of ES. This is equal to the rate of loss of ES, which is equal to the sum of rates -1 plus rate number 2. Okay, now rate -2 is going to be so small in comparison to rate 1 that it can be crossed out. Therefore, our double-headed arrow is going to be replaced with a single arrow. Okay, now on page 2, the same sequence above is written down for enzyme catalysis. And the steady state right here, equation where we have the rates forming ES is equal to the rates taking away ES. So this equation can be rewritten by swapping out rate values for their rate constants times the reactants for those reactions. Next, we can introduce an idea that our enzyme total is going to be equal to the enzyme free concentration that is not bound to substrate times the enzyme concentration that is bound to substrate. Okay, now E can be written as E total minus ES, and that can be substituted for E right here. Okay, now the right side of the equation is we're going to factor out the common term, which is ES, okay, on the right side. Now this previous equation, the left side of the equation is going to be expanded from the one above, and then we're going to factor out K1, okay, and divide both sides of the equation by K1, okay? That is going to lead to a combined group of constant terms that we are going to equate to the value Km, which we will discuss shortly. Now, Km is going to be substituted back into the previous equation right here for the group terms of constants. And the left and right sides of the equations are going to be rearranged right here. And then both sides of the equations are going to be divided by Km plus S, leaving this equation right here. Okay, so we just rewrote that equation, rewrote it above right here. So the speed of our whole process is going to be VO, okay? And that is the rate of formation of product, and that is going to be equal to K2 times our enzyme substrate complex. Now, what we're going to do, we're going to times this equation right here by K2 on both sides, okay? That is going to lead to this equation right here. Now, we can make the assumption that if our VO equals to Vmax, then our enzyme total is going to be equal to our enzyme, all of our enzyme, which is going to be saturated with substrate. So therefore, our Vmax is going to be equal to K2 times our E total. Okay? And so that term Vmax is going to be substituted for this right here. okay? And that leads to our famous Michaelis-Menten equation, okay, as shown. Lastly, we're going to briefly discuss the Michaelis-Menten constant, which is Km. So if Km equals to substrate concentration, then that value, substrate, is going to be substituted for our Km as shown, okay? So which leads to this equation here. And so our substrates are going to cancel out, which is going to lead to this right here, which we will left with Vmax over 2. So Km can then be defined as the substrate concentration, where our rate of reaction equals to half of our Vmax. So the lower our Km value, the better our enzyme is at working when substrate concentrations are small. Thank you.